All right, so now after talking in thorough details about the VAs, the vertical asymptotes, and the whole nature of a rational function, let's now advance to the next detail right here of a rational function, the intercepts. So just like any other function, being a rational function, it will have a graph, and as you have seen quite often throughout our earlier details discussion right there. And so now the graph on any rational function will at some point cross through the y-axis and cross through the x-axis, cross through the vertical axis, and cross through the horizontal axis. And so in that way, we are now learning how to find, and we're learning and we study some more about the vertical and the horizontal intercepts that come out from on a rational function. Okay, so I see the topic about intercepts as one subtopic as we are still going through this big topic that we're talking about all the rational functions. Okay, so now we specifically focus on the intercepts, that nature of what's in a rational function that gives these intercepts right here, the horizontal intercepts and the vertical intercepts. So if we strictly see this as just one detail regarding a rational function, one detail of the rational function, then some other professors may teach this earlier in the process of learning about a rational function. However, in my style of approaching this, I strictly see that it is extremely beneficial that we learn about intercepts of a rational function after you have learned about all the vertical asymptotes and the holes right there. Okay, and so it is highly, even though it's already in the lecture in a certain order, okay, but anytime that you randomly run into this part, I highly recommend that you've been fluent with the skills of finding VAs and finding holes, vertical asymptotes and holes of a rational function before we move on to being able to find intercepts of a rational function. Okay, but other than that, let's get on to that. Okay, let's get into the details understanding of how we can find intercepts. And so, just like how I was explaining, just like any other graph, we may have some vertical asymptotes, okay, but our graph in the end, our graph of a rational function may be asymptotic at some point, but it may cross through the x-axis or the horizontal axis at a few points, okay, and it may also cross through the vertical axis at one point. Okay, and so now needless to repeat so many times of this understanding, because it's the same understanding that we've learned previously throughout earlier lectures, not only just on the polynomials, not only just any function, but now generally as a rule of thumb, being at, so this point right here we call that it's a vertical intercept. Okay, vertical intercept. And then specifically, if we use in our work, if we use the vertical axis, if we label the vertical axis as the y-axis, then yes, we famously call that the y-intercept. Okay, which many professors set their students into that direction. Okay, and then same way right here, any of these values where the graph crosses with the horizontal axis right here, we may have multiple horizontal axes. We may have multiple horizontal intercepts. Vertical intercepts, there can only be one. Okay, and it comes straight out from the understanding about a function, not only just being a rational function, but on any function we only have one vertical intercept. Okay, but now for horizontal intercepts we may have multiple. Okay, so these are horizontal intercepts. All right, horizontal intercepts. And so now, if specifically we are labeling our horizontal axis here as the x variable, then yes, horizontal intercepts a lot of times are being referred as x-intercepts. Okay, and so x-intercepts we can have multiple places on the x-axis, on the horizontal axis, where our graph crosses through the x-axis, the horizontal axis, whereas for the vertical intercept there can only be one, and uniquely one. Okay, there can only be one. Now, when we get a little further into this, there may be time where there is none. Okay, there may be time for for rational function specifically, there may be case where there's none. So for vertical intercept, possibly no, possibly none, okay? And I will get further into that, but that's only for vertical intercept. So if there's one, there's only uniquely one vertical intercept. But then there's another possibility that your rational function, for rational function, there's a chance that there's completely no vertical intercept. Okay, and then we will get to further detail into that. So here I'm only giving a brief review. But now, with all of these details I've been briefing through right here, one general or one generality remains throughout the whole time so far, ever since we beginning out talked about graph of any function up until now. We've also gone through the polynomials and all of that. But anytime we're looking at, anytime our graph hits the y-axis, anytime our graph crosses through the vertical axis to call that point, to create that point where we call the vertical intercept, that point has to be famously known to have x value or horizontal value being 0. Okay, and then the other value is a y value. And that's why, a lot of time it's easier to stay with the tradition to call that the y-intercept, but more generally it's a vertical intercept. But strictly, the x value, the horizontal value, has to be 0. Okay, and so same way, now with these horizontal intercepts, on any of these horizontal intercepts, okay, the y value or the vertical coordinates have to be 0, and then it could be whatever there. So there could be, if there are multiple, then we label them x1, x2, okay? There's x1, 0. But it doesn't matter where they are, the y values, the vertical values are 0, okay? At those horizontal intercepts. All right, so that's everything we need that's all we need about the generality of these intercepts in order to carry it into our detailed study. That's coming right up right here. All right, so, and another little detail right here to mention. It's always easier to find the vertical intercept, okay, than finding the horizontal intercept. So allow me to start out and moving quick on finding the vertical intercept right here, because that's the easier part, easy to catch, easy to be done, okay. All right, so now as far as vertical, another subtopic, right, within our topic talking about the intercepts. So now this is a subsection of that. Okay, so vertical intercept. All right, so I don't need to write that as a plural because there's only either none or only one, uniquely one. Okay, so now let me promote a couple rational functions. Let me demonstrate the idea through a couple rational functions, and we will get to that quickly. We will easily see the idea right here. So how about the first one here is f of x equals x plus 2 over x squared minus 3x plus 2. All right. X plus 2 over x squared minus 3x plus 2. And then we have learned so much throughout our earlier discussion that, these are polynomials over polynomial, a polynomial in the numerator divided by a polynomial in the denominator. And it would be extremely useful, as we have seen in earlier thorough details learning right there. And so it's best that we can factor it out, even though we're not sure at this point what specifically do I need out of these factors yet. But we have seen that enough throughout our earlier work that it's best to put all of these numerator and denominator into factor form. Okay, so now I'm looking at the denominator polynomial here being factored into x minus 1 and x minus 2. Okay, x minus 1 and x minus 2. So now, again, vertical intercept happens at we have vertical intercept when x equals 0. when the horizontal value equals 0. So that's one thing we know for sure. All right, that's one thing we know for sure. So in that way, we're just going to easily to find a vertical intercept of this particular demo problem right here, of this particular demo rational function. I am simply just going to let x, okay, I'm going to let x equal 0. Okay, and so that means consequently the y value will come out being, the function value at x equals 0. Notice we have also prior to getting to this point right here, we've gone through looking at domains and vertical asymptotes and all that, and holes and all that. So one thing I know for sure, this x equals, because again, finding vertical asymptotes, finding vertical intercepts only happens when x equals 0. Only happens when x equals 0. I should have also used that term right here. Only when x equals 0. So now, one critical thing, we have to check and make sure x equals 0 stays in the domain. Or in other words, we have to make sure f of 0 is defined. That's why I mentioned a little bit about the domain here. This function in particular has the domain, and interval notation is a little too long for me, so just allow me to write in the shorthand notation right here. Anywhere except 1 and 2. The domain is any x value except 1 and 2. Because right out from out, these are the zeros of our denominator. Okay, so in that way, now x equals 0 is surely other than 1 and other than 2. And so now we know that f of 0 will be defined. Okay, we'll have a defined value. So now I'm going to go ahead and proceed and calculate the y value. So once again, I repeat, the thought process here is that we have just now made sure, we have just now checked and double checked and made sure that x equals 0 is in our domain, in the domain of the function, because x equals 0 is other than 1 and as well as other than 2. And so that means f of 0 will be a defined value, will have a final calculated value. Okay, and so in that way, I'm going to easily substitute 0 into the function. The rule says every input we're going to add 2 and divide that by, in the denominator, 0 minus 1 times 0 minus 2. All right, and we easily get this value here. So that's a 2 on top. There's a negative 1 times a negative 2. That's giving it a 2 here. Cancel out a 2. We're ending up with a 1. All right, so for this problem right here, we have a y-intercept. Okay, as far as conclusion, we have a y-intercept at 0, 1. That's our answer. Okay, and that's how easy that is. So before I rush into the next demo problem, I'm still not gonna make, I still did not make any generalization yet. Okay, let's see the result here. Let's confirm our result through the graph. And so when it gets to these functions, starting with the polynomials and now moving on to the rational functions like that, then it is extremely beneficial that we're working anything side by side with a graphical look at the graph like that. Okay. All right, so now here's my empty graphing space with decimals. The function we had on the board as a demo function is as following. All right, so this is our graph right here. This is the graph for our function. All right, the graph of x plus 2 all over x squared minus 3x plus 2. All right, and so now once we're upon having that graph right there, this point that just now popped out is our y-intercept. All right, and clearly the picture is showing it. Now let me put it in a much closer zoom that anyone viewing the lesson can have a better view of that. All right, so this point right here is right where my graph is going through the y-axis, the vertical axis in this case, and that's why we call it's the vertical intercept. And so now as far as the coordinates, allow me to show the label. Okay, so the label of the coordinates, just like how I was explaining, x value or the horizontal value has to be 0 here. And then the vertical coordinates, the vertical value of this point is whatever calculated on the board earlier. So consistently here it's showing 1. Okay, and that came out just reflecting our calculation here. All right, let's look through another demo problem like that. Okay, so the only rule of thumb here, vertical intercepts only happens when x equals 0. It's the way it is. It's the way it is. All right. And so now let me come up with another function right here. And how about we have x plus 5, okay, and we're dividing that by x squared plus 2x. X squared plus 2x. Okay. Now, only when x equals 0 we will have a vertical intercept. Okay. So after seeing the first demo problem, somebody start forming into a routine. I agree with you. Let me repeat that step right there. I'm going to start out by letting x equals 0, because this is also pretty standard with the way we have found vertical intercepts on any other function we have learned prior to this point. Anytime finding vertical intercepts as a standard work, okay, we're just going to start out by letting x equals 0. Okay, and that's why, like I said, only have vertical intercept when x equals 0. So it makes perfect sense, and being, on the standard, let x equal 0. So now y value will be computed as f of 0. Okay, because now we only know that x value at the y-intercept must be 0. But now to find the y value, to complete the point, to complete that intercept point right there, we have to substitute x equals 0 into the function. Okay, and now we're ending up with, the rule says 0 plus 5 as the input, plus 5 for every input, and we're dividing that by input square plus 2 times the input in the denominator. All right, and start proceeding your calculation carefully. All right. So now in my calculation, at least, this is what I see right here. I'm ending up with numerator is going to give me a 5. Okay, denominator is going to give me a 0. And oops, this is where we're actually ending up with an undefined value. So in other words, right here we have no value for this output. We have an undefined output right here. How unfortunate. Vertical intercepts only happens when x equals 0, or only when x equals 0. But then for this particular rational function, it looks just usual like any other rational function. Okay, and it really came out from my own creativity. But this one here, unlike the earlier demo problem, this one did not come out with an output y value. Indeed, when we substitute this into the function, we ran into an undefined value. Okay, so the step that I was missing compared to the demo problem I did earlier is that I forgot, and on purpose, I purposely forgot to double check this with the domain of our rational function. It is extremely important that when you're working with rational function, you have to constantly double check with the domain of your rational function. Okay, of your current rational function. So now this rational function, now if we put that in factor form of the denominator, x plus 5, well, x plus 5 in the numerator is already a linear factor by itself anyway, so there's no further step to factor this. So in other words, it's already a factor on its own. The denominator can be further put into factor form as x times x plus 2. Now that mystery became clear now at this point, explaining why we had an undefined, because in the way how we factor it out, we now notice this function has domain being any x values, or anywhere on the x-axis, anywhere on the real values except x equals 0 and except x equals -2. All right, so how unfortunate, I said earlier, how unfortunate, simply because vertical intercept can only happen when x equals 0, only happens when x equals 0. But for this particular problem, for this particular rational function, x equals 0 is excluded out. X equals 0 is excluded out from the domain. Okay, from the domain, and that's what explains for having an undefined output y value right here. So now, as what do we conclude for a case like this? We're saying that there is no vertical intercept. All right, no vertical intercept, and this is why I was saying this earlier in my brief introduction, that for a rational function a little more special than any other usual function. For rational function, there can be a possibility of no vertical intercept, no vertical intercept. This is the case right here. Okay, so let's quickly demonstrate the idea here through the graph. Like I said, hopefully I'm really trying to make that progress where every single step I'm moving right here has a side-by-side graphical view like that. Okay, so all right, so now on the empty graphing screen here, my empty graphing space with decimals, this is now our graph for x plus 5 over x squared plus 2x. All right, and so combined with our past learning regarding the rational functions, then this particular function here has a vertical asymptote. And we have spent a good amount of time talking about vertical asymptotes, discussing in details about vertical asymptotes. So unfortunately, for this particular function, x equals 0. X equals 0. The only place where we can have a vertical asymptote, but right at x equals 0, or the y-axis itself is now the vertical asymptote of our function, of our rational function here. So now in a complete full screen view right here, again, let's have a look. So x equals 0. This y-axis right here, x equals 0 is the equation of the y-axis. But now our graph is asymptotic to that, meaning it will never even hit, it's never gonna even hit the y-axis. And so this is the reason why, now back to my conclusion, now I'm so firm that I can say there's no vertical intercept for this particular rational function. All right, so that's the whole idea. So now we are ready to come up with a generalization, a formal generalization, and then we're gonna use that as our guideline for any actual example in terms of finding the vertical intercept on any of our rational function. And you can, by the time I finish with the 2 demo problems here, you already got a good hang of that. I believe so. All right. All right, and so now as far as finding the vertical intercept, okay, we have the following generalization right here. So this is what to remember for vertical intercept. All right, there can only be one, of course. And so now here's how I'm saying it. Except x equals 0 is a 0 of the denominator, okay? Except for that case, then the vertical intercept of a rational function, any rational function, is the value x equals 0, comma, the function at the function at x equals 0. But that's why I said except when x equals 0. So other than that case right there, okay, except x equals 0 is a 0 in the denominator, because rational function is all about a polynomial over a polynomial. So 0 is the value, again, that review from our polynomial. 0 is a value where it causes our polynomial to equal 0. But so now except x equals 0 is a 0 of the denominator. Okay, or you can also say except x equals 0 is a vertical asymptote. That's another way of saying it. Is a vertical asymptote. Okay, that's another way of how you can see that. Just extra note for us. But formally speaking, it's a 0 of the denominator. Then the vertical the vertical intercepts. You can see that I keep mistakenly the two names here quite a few times already, because I got it so long into working with vertical asymptotes just right before writing recording this lecture in particular. So the vertical intercept of any rational function, just like usual, we're gonna just be x equals 0, comma f of 0. But then, like I said, it's only working anywhere except the case where x equals 0, being the 0 of the denominator. So if that really happened, if that case happened, we're gonna say no vertical, and admittedly this is my own style of wording it a little bit. So no vertical intercept when x equals 0 specifically. Okay, or just a little more properly with the grammar right there, then there is no vertical intercept when x equals 0, but just to keep it short and understandable, okay, in a limited space like this, allow me to write with informal the grammar right there. All right, so that's one general guideline right there. So this is generally how we find it. Let x equal 0, substitute that in the function. That's our y-intercept. Okay, but this is only working for any x value except x equals 0 being the 0 of the denominator. So it works anytime except x equals 0 happens to be the vertical, the asymptote. So in that case, if that's the case right there, we're going to say, so no vertical intercept when x equals 0 is a vertical asymptote. Okay. So in this way right here, now, so in this way, in the way how I see it, so generally it works just like when we find vertical asymptote, vertical intercepts at for any other function. Okay, we're gonna let x equal 0, and we're gonna plug that into our function. We're gonna plug that into our function to find the output value. But then this generality only works when except the case only work anywhere except the case x equals 0 is a vertical asymptote of our rational function, because rational function has that vertical asymptote crisis right there. Okay, and or except that case where x equals 0 is a 0 of the denominator. These are the two equivalents. Like, this is more precise, because when we talked about vertical asymptote, there could also be time where a vertical asymptote appears to be a whole. All right, so in that case, most precisely, except x equals 0 is a 0 of the denominator, then we can always find the vertical intercept as usual. Okay, and now in that unfortunate situation where x equals 0 truly is a vertical asymptote or a whole, or in this case, allow me to modify my statement here a little bit, is a 0. Okay, that's the most precise way, is a 0 of the denominator. Okay, so if that unfortunate case really happens when x equals 0 is a 0 of the denominator, then we're going to have to say there's no vertical intercept. Okay, all right, so now with this as a general guideline, and I believe anyone viewing the lesson currently, as soon as I finish with the two demo problems, you wouldn't even need to proceed to this. But that's just an idea about we put in a formal generalization. So now we're going to use this generalization to push that into a few examples, a few example problems, so that we can start setting ourselves into a routine of how we find vertical intercepts. That's all. Okay. All right, so here we go. And so in this way, I am going to have just a short example here. We don't have to work through too many problems because you will get a good hang of that after just only a couple sub-problems here in this example. So example 5. Let's now find the vertical intercept. Find the vertical intercept of the given rational function. All right. Didn't have to be plural there. All right, just simply find the vertical intercept of the given rational function. Okay, so now again, just like what I was explaining earlier, vertical intercept, once we found it, there can only be one, and there's a possibility that there's none. All right, so let's dive in. So how about part A right here? Our rational function is given to be, how about or of x equals, and so here I'm looking at x minus 1 divided by x plus 5. Okay, one simple one, nice and short. So now what's to be cautious about is before we really get into letting x equal 0, it's best as a common practice, it's the best practice to do the following. Check with the domain. Check with the domain, okay? So, and the domain is directly related to all the zeros in the denominator. So in other words, think about, check with the domain or think about the zeros in the denominator. So zeros in the denominator, okay? Or another way of saying domain or anything like that. So 0 in the denominator is a -5. That's what happens. So 0 in the denominator means it could be a vertical asymptote there, or it could be a hole there, or it just be excluded out from the domain. But the good thing is we only found 1 0 in the denominator for this rational function. All right, so in that case right here, we know immediately that we will have a vertical intercept because x equals 0 is not a 0 in the denominator. That's what the generalization I wrote on the other board is all about. So now I'm going to go ahead and let x equal 0 because now we know we will have a value. We can move freely with letting x equal 0, substitute that into the function. So now I'm going to have y value will come out as r of 0. That now gives me 0 minus 1 as the input. 0 as the input, minus 1 divided by 0 as the input, plus 5 in the denominator. And now we're looking at -1/5. -1/5. All right. And yes, ladies and gentlemen, as far as the vertical intercept, as far as the y-intercept, okay, as a complete point right here. When it comes to y-intercept, I tend to write the complete coordinates pair right there. So 0 for the horizontal value for x, and then we have a -1/5 for y. This is our y-intercept as a final conclusion. All right, and once again, let's hop over to our graphing utility with decimals at my computer station right there to double check with this using the graphical view right there. Okay. All right, so right now with my empty graphing space here, okay, the function that we were working with is now here. This is the graph for f of x equals x minus 1 over x plus 5. Okay, and so specifically when x equals 0, we have a point right down here that just now popped out, okay, to be our y-intercept or to be the vertical intercept. So now let me put it in a zoom. So this is a rational function. So we do have a vertical asymptote here, but right now that's not what we need, focusing on the vertical asymptote. So I'm not going to ignore that. I'm going to turn my focus to this point right here, being the vertical intercept of our graph. Okay, and so right here now let me show the label of that. The label is showing 0, comma, negative 0.2. Now decimals can only show these values in decimals, so that's what it looks like. This is really negative 1/5 right here, equivalent to negative 1/5. All right, and that agrees with our calculation of the y-intercept. Okay. And so now let's work on another function. And the point now is that no matter how complicated or how simple the rational function looks, okay, there's only one rule over here. We're going to let x equals 0 and substitute that into the rational function. And if unfortunately it runs right into the exception, it runs right into the exceptions where, hey, we don't want x equals 0 to be as a 0 in the denominator, then if that case really happens, if we run into that conflict there, and we're going to say there is no vertical intercept. That's all there is. Okay, so I'm going to keep this list right here because I'm going to throw in some other list. All right. So part B, let's look at f. How about q of x right here equals x squared minus 4x plus 1, and I'm dividing that by x squared plus 8x plus 7. Okay, x squared plus 8x plus 7. Okay, so now for this function right here, for this rational function, yes, two polynomials, but what's more important is that we need to focus in the denominator to first identify all zeros in the denominator, because now in our next step, when we get into finding the actual vertical intercepts, right, and we need to make sure x equals 0 is not among the zeros in the denominator, and that's why it's always best to list down immediately the zeros in the denominator. Okay, so in this case right here, now we can quickly see on scratch work, this can factor into, so x squared minus 4x plus 1 can factor into x plus 7 times x plus 1. So these two factors in the denominator are responsible for two different zeros in my denominator. So I have one at x equals negative 7, and I have one at x equals negative 1. So I have two zeros in the denominator. So, but now that tells me that x equals 0 is not among the zeros here in the denominator. So now we one more time after a problem, part A right here, then now we are able to find the vertical intercept here. So now the vertical intercept, we're going to start by letting x equals 0, and then we're going to calculate the y value as q of 0, and we multiply, and we're doing that by, so here in factor form it's even making it easier to do the calculation. So I have input square minus 4 times the input in the numerator plus 1, and we're dividing that by, now I use directly that factor form of the denominator, 0 plus 7 times 0 plus 1. Okay, 0 plus 7 times 0 plus 1. All right, so now in that way my final output will be, and we know for sure that we will have a defined final output because x equals 0 is not among our zeros in the denominator. All right, so that confirms our steps of how to find vertical asymptote. So now, vertical intercept. Okay, and so now 0 squared minus 4, 0 plus 1, and all of that divided, we really end up with 1 over 7. Okay, 1/7. That is our y-intercept. But formally speaking, I can save this. I can put the final answer as so y-intercept, okay, is at 0 for x, comma 1/7 for y. All right, and this is our final answer. All right, so that's the y-intercept that we have found. And once again, let's one more time use the graph to double check with our results right here. All right, so on my empty graphing space with decimals right here, this is the graph for our function x squared minus 4x plus 1 all over x squared plus 8x plus 7. Okay, so this is, we do have a couple of vertical asymptotes, but Now right at x equals 0, we have this intercept right here. Okay, we do have a vertical intercept. And so now I'm going to put in the actual value right there and with a label. Okay, so the label is here, 0, comma. Now decimals can only show the value in decimals, but really it's 1/7. Okay, this is 1/7. All right. And now let's look at another one for our in our work to find vertical intercept. All right, so for the next function in our example 5 here, let's look at part C. So I call that q of x again. Okay, and here I call that how about x squared plus 1, right? And then we divided that by x squared minus 3x. All right, x squared minus 3x. All right, so with this function right here, once again with this rational function, and for any rational function, we get into that routine of identifying first the zeros in the denominator, because those are so critical. The domain is anywhere excluding those zeros in the denominator. Okay, and we will have vertical asymptotes and or holes around those zeros in the denominator. And now when we get to vertical intercept, we sometimes can have no vertical intercept if our x equals 0 is one of the zeros among one of the zeros in the denominator. Okay, so in that case, let's list down all the zeros in our denominator. So in factor form, this can factor into, so x squared plus 1 is in the numerator. This factor into x times x minus 3, and we're starting to see some lead right here. Okay, so now as far as the zeros in the denominator, I do have a 0 at x equals 0 for our denominator. I have another 0 at x equals 3. So I have 2 zeros in my denominator. But now for this, the only way to find vertical intercept is to let x equal 0. But then x equals 0 is unfortunately one among our zeros of the denominator. So the straightforward final answer here, the straight final conclusion here is no vertical intercept. All right. No vertical intercept. All right. So now that's how we've done. And that at least just 3 problems. Admittedly, I didn't do too many problems, and they went by pretty quickly right there. All right. And so now I'm going to quickly show this the graph of this function on decimals right there. And then this is about the end of our example 5 right there. We already set for ourselves into a solid routine of the work, how we find the vertical intercept on any rational function. All right, and now on our graphing space with decimals right here, this is the graph for x squared plus 1 all over x squared minus 3x. All right, and so now right here I notice we do have a vertical asymptote at x equals 0, which unfortunately the case where which unfortunately the x values that we need to substitute into our function to find vertical intercept. So we won't have, this is the reason why we won't have any vertical intercept for this particular function. So let me show the vertical asymptote here. So the vertical asymptote is right here at x equals 0. Okay, this also means we have a 0 in the denominator at x equals 0, and that's the reason why our graph obviously is not crossing through, is not even going to hit this vertical line right there, okay, which is namely the y-axis. All right, and so now we are going to explore the horizontal intercepts of a rational function. Okay, so this is a subtopic of a little bit larger subtopic. So horizontal intercept. So we just, now when it gets to horizontal intercepts of rational function, we only need to focus on being able to find it, how to find it, and that should be all. Okay, we won't have as many detailed discussions about the behavior of those horizontal intercepts as compared to those the details we've learned back in the polynomials. Okay, so something for anyone to know a little bit ahead of time before we get into the actual problem. Okay, so now horizontal intercepts. So let me now start bringing up a few demonstration problems again. So the idea, as you have already seen, we have a rational function and maybe some asymptotes, vertical asymptotes, okay, and then the function may be having some asymptotic behavior around these vertical asymptotes, but in the end there could be or there could be not. Okay, there may be or there may be not some intersection points where the graph is crossing through the horizontal axis, and so we call these the horizontal intercepts. Okay, so now like I said earlier, here I drew a picture where there were some crossing points, but like there could be also cases where the graph just does not cross at all. Okay, and so there may, and that's why, like I said earlier, there may or there may not be horizontal intercepts. But now we're gonna learn one solid technique one solid method that find and keep track of all horizontal intercepts. Okay, and once we're done with that solid method of how to find all the horizontal intercepts of a rational function, and we should be good with our discussion about the horizontal intercepts. Okay, and one more thing to know: just like any other horizontal intercepts, or the x-intercept, okay, there may be multiple intercepts as well. So there could be none, okay, there could be uniquely one, or there could also be multiple. But then doesn't matter how many horizontal intercepts there are. Once we have found any horizontal intercepts, then it must be in a form of some horizontal value for the x, but then 0 value for y. Okay, 0 value for the vertical coordinates. Okay, so I'm indicating one pair of value here, but for any of these horizontal intercepts, as wherever they are on the x-axis or on the horizontal axis, we indicate them with the value x right here, but then their y value, their vertical value, has to be 0. Okay, that's one fundamental understanding. So just like what we've learned from the polynomials, just like what we've learned about any other equations prior to this class, any other functions, zeros before we get to this class, any other horizontal intercepts that we've learned from before this class. All right, so now we really are ready for getting into some demonstration problem. And so there are indeed, as a matter of fact, I do have to admit, there are going to be quite a few different cases before we would be able to formulate into a generalization. But the ones we form into a generalization, then it should become, we will have a formal, a solid, definite method to find horizontal intercepts. All right. So now the first demo problem I want to bring in, and now let me erase this subtitle of our discussion here. Let's consider I want to consider that function. How about f of x equals there's x squared plus 5x plus 6. All right, and then we divide that by x cubed minus 7x squared plus 12x. All right, so here's our rational function right here. So if you recognize it, or you may not recognize it, but this indeed comes from one of our examples problems previously. Okay, and now I'm using this particular function again, because it has all of that feature right there. Okay, so it's a rational function. So now from the experience we have had in the earlier examples, at this point in this lecture, sadly I just don't remember any further which example that was that had this particular example, this particular problem right here. But now, let's say at this point in our experience learning, and even we have already gone past finding vertical intercepts, then now it's always best to factor out. It's always best to factor out completely both numerator and denominator. That's now going to be one highlight that I never mentioned this before until this point. And so now after you have learned fluently and become fluently with how to find your vertical asymptotes, the wholes of a rational function, okay, and then even past that point where we've had the vertical asymptote, and especially once you have already learned about domains of a function, and now it is extremely a good idea, or it's a highly recommended practice to factor out completely both numerator and denominator of your rational function. Okay, so now in that way, this is what I noticed. So f of x here, our current rational function, can be factored as now the denominator, we have seen that before from earlier example prior to this point. So it was x as one common factor, and we can easily see that right from here. And then we can additionally factor the remaining into x minus 3 times x minus 4. Okay, so this bottom denominator, this bottom polynomial, this denominator polynomial over here is factored into this form right here, into this factor form, 3 distinct linear factors. Okay, and then now, as I said earlier, it is best, really a highly recommended practice right here, factor completely both numerator and denominator. So in this case, I am going to factor out that numerator as well. Even though maybe when we were doing this particular problem in the earlier example, we might have not done that yet. But this time now, to really get into a good common practice, we always gonna put our numerator and denominator into factor forms completely. So that top one here is going to be x plus 2 times x plus 3. And again, like I said, somewhere here and there throughout this lecture, allow me to assume that anyone viewing the lesson here has already been fluent with the factoring skills that you have learned either from the earlier course or from, some earlier lecture where I keep introducing some of the review of these techniques right here. Okay, so now my numerator is factored into x plus 2 times x plus 3. Two distinct factors here in the numerator. Okay, so in the end, that's the way how how a rational function is. Both numerator and denominator are all polynomials. Okay, so now, right at this point, I am not going to rush into showing a technique immediately, but now that we have had our rational function in successful factor form, in complete factor form for both numerator and denominator, I'm actually going to approach it graphically first. Okay, I'm going to just show a graphical demonstration. Okay, because that will make the story clear, and then from looking at the graph, we're going to be able to conclude for ourselves and formulate into a solid method. Okay, so right now that this is all we've done algebraically. We've factored our rational function, both top and bottom, into complete factor form. Okay, so now on my graphing space right here, the empty graphing space with my Desmos graphing utility. All right, so here we go. This is our graph for the function that I wrote on the board. Okay, this is the graph for f of x equals x squared plus 5x plus 6 all over x cubed minus 7x squared plus 12x. Okay. This is the graph. And so from our previous work, in exploring the details of this function, we have already found that this function, and we are fluent. And at least if anyone did not remember, then you can always apply the skills you have learned into doing this again. But this function is clearly having 3 vertical asymptotes. One of them is at x equals 0. So now allow me to put that in. And then we have another one at x equals 3. Now allow me to put that in. And then it looks like there's another one at x equals 4. And now allow me to put that in. All right, so 3 vertical asymptotes being shown in the picture here together with our graph. But now this is looking, vertical asymptotes is not what we're looking for. So now I'm going to zoom it in even closer. So right now in this middle body of the graph right here, we don't recognize anywhere, doesn't look like there's anywhere that the graph is crossing through the horizontal axis. Okay. And further, it looks like right here the graph is not going to cross through the x-axis, and no matter how far. So it seems to keep getting lower and lower, and we will get to that behavior later on. But right now, if I keep zooming in, there's still some difference, some noticeable difference once we zoomed in close enough. Okay, but there's still some difference between the graph and the x-axis. So in other words, what I'm saying here is that there won't be any horizontal intercept in this area of the graph. So we've looked at the middle part of the middle body of the graph. We've looked at the right side, and we haven't recognized, we haven't spotted. So now let's zoom in. Let's put in some zoom and to recognize something else further. Okay. So the graph here this time is indeed now right here. I see something funny. Okay. And thankfully that we have powerful enough the graphing utility here with decimals, because what I see here is that there's one portion of the graph seems like it's below a black line. This black thin line, hard to recognize right now, is our famous y-axis, and this part in red right here is the actual graph of our function. But then at some point it does look like the graph in red crosses through the line being the x-axis here. So now if we zoom in, we put in some really good zoom, it doesn't look like it's happening at -4. That doesn't look like it's happening at -4, but rather it's happening at, and I'm talking specifically now about the crossing nature, because I doubt that there's a place where the graph crossed through the x-axis. So now here's what I see. All right, so let me now make it real clear with this point right here. So now with this point particularly, so there's this point particularly at when x equals -3. Let me now show the label. All right, so now with that, this point is on the graph. When x equals -3, we found out the y value, the vertical coordinates, is 0. Okay, so now that means we have found one. So let's get back to the board. So from this function, and of course, like I said, we completely rely on the graph so far to make an estimate. So right now, everything it's completely okay that you're seeing this as I'm showing an estimate of the horizontal intercept. Okay, so it looks like I found through the graph horizontal intercepts. Okay, from the graph, and I found x equals -3. X equals -3. That point was shown on the graph. And let me put that graph here together with our board here so that you can notice. All right, so x equals -3. That point being highlighted, being displayed with the label right there. So at x equals -3, we have a horizontal intercept. That is one place we already spotted where the graph went through the horizontal intercept. Okay, and so now let's put that here. Let's explore for another one. Let's find out for another one. And so now one more time back into the complete full screen view of our graph here. I am going to point out another one. It's hard to see, admittedly. Sometimes it's hard to see. That's why eventually we have to use a solid algebraic methods to find the actual the horizontal intercept of a rational function, because we cannot just keep relying on the graph, because see right here, obviously with this graph right here, it's not doing a well done job. It's hard to recognize. Okay, it's hard to recognize this point already, and then it's even hard to recognize the other point, even though right now I'm in that position of being the professor, so I prepare these the functions a little bit ahead of time, so I kind of knew. But think about if you are starting a rational function from scratch, estimating from a graph is definitely not the best idea. It may work sometimes, but it's not the best idea. Okay, so in that way, now let's still look at the graph to estimate a little further. I know we're still cranking a little too much right here, but then once we recognize it, it's going to be better. Okay, so I am going to see another point. So now allow me to hide this point away. And now I am going to look at another one. So now this time, let me show you another one for here. Indeed, that point there now would label being displayed together with that point. We actually now recognize there is another horizontal intercept here. Okay, so now back on my board, and I'm still keeping the graph here. We found, aside from x equals -3, we found another one. So at x equals -3 and x equals -2. Okay, so we found two. And think about if you are a student currently learning in this lesson right here, then it's completely so far that I'm leading you into seeing these. But think about if you are starting from scratch right there, admittedly it's very hard to recognize these two. Okay, so there has to be something in the function that we can rely to, instead of looking at the graph, to quickly and easily identify the horizontal intercepts. Otherwise, if we keep relying on the graph, it's going to be a very challenging work out there anytime it comes to finding horizontal intercepts. All right, and so now, and I see if we're working with this function from scratch, then outside of these, and if we only would outside of these two horizontal intercepts and without a proper or a solid algebraic method, then it's gonna be a little unclear whether we're gonna have a third intercept or not. Okay, because right now, yes, I led the way and I pointed it out. I pinpointed that there were these two, but anyone is already gonna be having that worry in mind that aside from these 2 points right here, are we gonna have any more horizontal intercepts out there? Because the graph is very hard to read right there. Okay, and so that's the reason why we need to develop a method that help us quickly identify and then easily identify those horizontal intercepts. Okay, so now in this case right here, here's what I'm seeing, and I'm not saying that we're done and ready for formalizing that method yet. Okay, but at least for this demonstration problem right here, I can guarantee you, but not because I'm the teacher. It's just right now I created this problem myself, so I knew it. Okay, but if anyone else is giving me a problem that was not the one I defined right there, then I'll have to rely on a method. But right now, in the way how I see, if I was a student, the observation here is telling me that x equals -3 is indeed kinda. It rings a bell. It's right now I only treat that as a discovery work, and we're trying to explore the things around the further details here. So x equals -3 being claimed as the horizontal intercept. It looks like this x equals -3 is corresponding to that factor x plus 3 in our numerator polynomial. And that's the reason why being able to factor out recommending any of my students to factor out completely top and bottom of any rational function is just my own style when it gets into doing horizontal intercepts for any of the work right here. And then once we're done with this lesson right here, it's always a good idea to start out factoring out completely numerator and denominator for any rational function. Okay, because now that shows immediately some correspondence, some relationship between this factor here in the numerator and that horizontal intercept. Okay, is that the same case again when it gets to the other horizontal intercept? X equals -2. Well, the graph showed us, we spotted that from the graph, but it looks like it's that same rule again. This x equals -2 being our horizontal intercept, it came out, it looks like it came out from this factor over here being x plus 2, that unique factor. All right, so we start having some idea. Okay, we start having some idea. It looks like these horizontal intercepts came from the, well, informal term, because in the end these are polynomials. The numerator and the denominator, they're all polynomials. So now if we're simply looking at this numerator here as a polynomial already in factor form, then any one of these so far looks like a zero of the numerator. Okay, so let's just write down that observation. So now I'm just going to write down the observation. I'm not making any formal conclusion yet, and we're not going to formulate that into any generalization yet. Okay, but observation coming right from this problem, and after looking through the graph that that allowed us to spot out these two horizontal intercepts here, then I'm going to see that what we notice here is that horizontal intercepts. Okay, so this is what I noticed. All right, this is what I noticed, that horizontal intercepts, okay, are at zeros. Okay, zeros of the numerator. All right, that's one little observation. I'm not saying that it's the hard truth yet. Okay, I'm not going to say that yet. It's just an observation we drew right out from this particular problem right there. But who knows? This is just the first problem throughout our entire lecture so far that we're hunting for horizontal intercepts. All right, so let's look at another one. So everything I see here, let's end that here. Okay, horizontal intercepts seems like for this problem the horizontal intercepts are right at the zeros of the numerator. So throughout the whole lesson so far, the entire lecture about the rational function, we've been mostly focused to the denominator. The denominator polynomial has been, brought to our attention, most frequently so far. And now all of a sudden, this is our first problem where we start getting some attention on the numerator as a polynomial in complete factor form. All right. But that's not all the details yet, so that's why I don't want to rush into seeing this as the final hard truth about horizontal intercepts. Okay, let's move on to another demo problem right there, demonstration problems, and we're gonna repeat the similar thing. I'm gonna write down the function, and then this time, how about for simplicity, I will write down the rational functions in factor form. All right, already in factor form, and then we're gonna use decimals again, the graphing utility, to find and to estimate. Finding is not the correct word yet. To estimate as many as we can the horizontal intercepts. All right. So now, how about I'm going to erase this? Okay, and I'm going to also erase this observation here. Okay. All right. So let's now. We're pretty much going to repeat the similar kind of steps right here, and so that's why I can retain some of these writing on the board. So the next function I would like to introduce here is how about f of x equals, so now in complete factor form, and I have mentioned this already, even if it was not nice and it was not given as a factor form, we should, as something that's highly recommended, we should factor out completely the numerator and the denominator, okay, of any given rational function. That is one good experience that we've learned up to this point. So now, how about I'm going to give a case where that effort has been saved for us right there. So x times x plus 2 all squared. Okay, and we divided that by x minus 1 times x plus 1. And indeed, how about I prepared this x plus 2 all squared in the denominator. So this is a rational function. Both numerator and denominator are all polynomials. Okay, numerator and denominator are all polynomials. And this time, like I said earlier, I purposely brought in this the form of the rational function where both numerator and denominator are already in factor form. Okay, so now in that way, let's recognize our let's look at our graph. Okay, let's look at our graph to recognize or to estimate our horizontal intercepts. Okay, and so I don't need any more space here to write down the factor form. So in that way, I'm gonna get my list of the horizontal intercepts a little bit further up. All right, so now I'm going to turn over to decimals. All right, and now this is our empty graphing space in decimals graphing utility. All right, so now this is the graph for the actual graph for our f of x, being x times x plus 2r squared divided by x minus 1 times x plus 2r squared. Okay, we have that graph, and furthermore, in our experience that we have learned, this graph right here, and you should be able to see the explanation already, but this graph further has a hole on the graph at x equals -2. All right, and then so needless to say, this graph here trivially is showing a vertical asymptote right at x equals 1. So all that information here is consistent. All that information here is consistent with our graph that was written down on the board earlier. So we've learned from our vertical asymptotes and holes that because this one right here could have been vertical asymptotes, but the factor will eventually cancel out completely. And that's the reason why only that x minus 1 factor remains in the denominator responsible for the vertical asymptotes here. But this one here, which could have been a vertical asymptote, now became that hole on the graph at x equals -2. So as far as, or in another way of saying that this function right at start, before I did any simplification, before I did any cancellation of the common factor, then we found two distinct zeros of the denominator. Okay, so we need to always ensure x is other than 1 and x is other than -2, because these two values, they are the zeros of our denominator. That's just a quick little scratch work right there. Okay, because I don't want to get too far back into writing down the formal, listing down the zeros of all the denominator. That's what these are. Okay, and that's the reason why we have x equals -2 as being a hole there on the graph. We have a hole on the graph at x equals -2, and we had a vertical asymptote at x equals 1. Okay, but now our goal here is to look at the graph, to investigate the graph and estimate our estimates to find out any horizontal intercept anywhere on the horizontal axis where the graph is crossing through the horizontal axis. Okay, so now on the board, on the graphing space here with the graph. So with the graph here, it's actually showing that the graph is only crossing through or is only hitting through the x-axis, the horizontal axis at x equals 0. Okay, so allow me to show that point and make it real clear right there. All right, so just now that point has popped out. This is the point being our horizontal intercept here. And let me show the label. Okay, so right at x equals 0, and of course the y value is equal to 0 over here. Right at x equals 0, y equals 0. We have a horizontal intercept, okay, right here. And so now I need to bring back whatever observation we've had in the earlier demonstration problem. I thought we noticed that horizontal intercepts are at zeros of the numerator. This is what we made as an observation after the first demo problem. Horizontal intercepts were observed to be at the zeros of the numerator. That was what we observed from the earlier demonstration problem. So I thought, right, and naturally any one of us would think that we can carry that same observation, and we want to see if that observation is still the same, still being true here in this other one, in this next demo one. So it looks like, yes, we have found, and I pinpoint that x equals 0. We found one here. From decimals, we estimated this. That agrees with the observation we've made. That agrees with the observation we've made, because x, when we looking at this here, this x in the numerator, after the factor form, like that, once we factor the numerator, this x is equivalent to x minus 2 as a factor, as a distinct factor. So yes, this x right here is responsible, or it looks like it's the factor that's corresponding to this horizontal intercept that we found. But so wait a minute, if we follow with this observation that we have done from the earlier problem, then technically aren't we supposed to have another one at x equals negative 2? And I'm putting question mark there. So what about the x equals negative 2? Because x equals negative 2 is also a 0 of the horizontal, also a 0 of the numerator. But how come the graph just does not show it this time? All right, and so now we're going to look a little further into the graph again, and recall that I showed that hole on the graph earlier. All right, so back on the graph, let's now pay attention to the hole right here. The hole on this graph happens right at x equals negative 2, right at x equals negative 2, right here. Okay, and so in that way, here's how I see it. We had hole at x equals 2 because, see, in our understanding from the previous discussion about vertical asymptotes and holes like that, then at x equals, if x equals negative 2, or x equals negative 2 is also a 0, in the denominator. Okay, and so at that 0 at the denominator, x equals negative 2 being the 0 of the denominator, sadly this factor cancel completely with that x plus 2 right here and became a hole. That's how we had that hole right there. But more generally, I see that the hole here is indicating that x equals negative 2 is also a 0 of the denominator. Okay, what we observed earlier, horizontal intercept or at the zeros of the numerator. But now in this case, there's a little problem that some of the zeros in the numerator coincide, right, or happen to be the same with some zeros in the denominator. That's what happened in this problem right there. Okay, and then in this case, the 0 from the numerator and the 0 in the denominator gave that hole right there. Okay, and so the reason, so now all I'm trying to explain now is that the reason the graph did not show this x equals negative 2 as an intercept, because this point was, okay, x equals negative 2 is also, it's already a 0 of the denominator. It's already a 0 of the numerator, I meant. Okay, but now it's also a 0 in the denominator. Okay, and this is the reason why we have to cross x equals negative 2 out. We cannot take x equals negative 2 as a horizontal intercept, because the idea of horizontal intercept is that the point needs to be there on the graph. The point needs to be solid point on the graph and be right on the horizontal line, horizontal axis. But at x equals negative 2, we have an empty point, according to what we have learned previously, right before getting into finding intercepts. All right, and so the only thing we blame why we don't have a horizontal intercept at x equals negative 2, even though it was a horizontal intercept, even though it was a 0 of the numerator, even though x equals negative 2 was a 0 of the numerator, but we had to cross it out. That's simply because it's this x equals negative 2, once again, is also a 0 in the denominator. All right, so we start forming into a better, or we start forming into a more definite criteria to find horizontal intercepts. But there's a little more, okay? So in this case, but once again, at least we had a good guideline right here. We focus horizontal anytime finding horizontal intercepts, we focus first thing, we focus right to the zeros of our numerator. Focus to the zeros of our numerator. And then it looks like we're gonna start filtering out. We're gonna start filtering out those zeros in the numerator that also coincide with the zeros in the denominator. Okay, we're filtering out those zeros in the numerator that's also a 0 in the denominator. It looks like that's the way we're being led into right there. All right, so we finished our demo problem right here. Okay, let's look at another one, still another demo problem. So in this problem right here, we only found one horizontal intercept, and the graph showed that this is the one. And then, even though there were two zeros for the numerator. Okay. Let's now come up with another one. And I would like to look at, how about f of x equals, allow me to write it in complete factor form again. So x minus 2 times x minus 3, okay? And then in the denominator we have x minus 2 all squared times x minus 1. All right, so this is our third demo problem, our third rational function right here, and we're trying to look for horizontal intercepts of this particular rational function. All right, so once again, let's look into our Desmos graphing utility at the computer station there. All right, so now on our graphing space with Desmos here, this is now our graph for f of x, okay, that rational function I had on the board right there. And in complete factor form, that rational function was x minus 2 in parentheses times x minus 3 all over x minus 2 all squared times x minus 1 in the denominator. And that is the reason why, from our past understanding, we know that we're going to have two vertical asymptotes here, okay? One of them is at x equals 1. The other one is at x equals x equals 2. All right. And now this time, looking at this graph right here, giving it a quick sweep left and right, okay? Then I spotted only one point right here, about only one point where the graph crossed through the x-axis, or the horizontal intercept, or the horizontal axis. Okay, so let's find out precisely what that point is, because we can never trust our own eyes looking at just simply at the graph, because right here, when I'm standing right here in front of the computer, I cannot tell whether it's a x equals 3 or a 2.9 or a 2.99. Okay, so let's tear down the value to make it really clear right there. All right, so now that's the point that I detected. And now with this point label over here, so now we recognize clearly we have a horizontal intercept right at x equals 3, okay, because the y value came down to equal 0. All right, but it looks like that's the only point. We don't recognize, because anywhere out here the graph seems to get down real close to the horizontal axis, but indeed it's just not going to cross through. And as a matter of fact, now once I keep zooming in, we can see that the horizontal axis is here and the graph is still above it. Okay, so now in that way, and just like what I said earlier, we already did a brief sweeping left and right of the graph, and we saw that this is so far this is the only horizontal intercept. Okay, so let's write it down as our as a way to document our observation. And so now we are looking at one horizontal intercept I found at x equals 3. Okay, so we found 1. We spotted 1 from the graph, just like that. All right, and then again, if we apply that observations we've made from the very first one and we already carried it through the second one, it was still true, but with some restriction. Okay, it was still true, but with some extra condition right there. Okay, and so, or maybe I should have said some extra filtering guideline right there. And so now, but once again, from the ground up, is this spotted horizontal intercept corresponding with any of our 0 in the numerator? Now I'm focusing on the numerator. And of course, this function here, this rational function here must have, this rational function has 0 in the denominator at x equals 2 and x equals 1. So in that way, as far as the domain, we need to be anywhere aside from anywhere except x equals 2 and x equals 1. Okay, so these were zeros of our denominator. And so now I have found the horizontal intercept happen at, I have spotted a horizontal intercept at x equals 3. So it looks like x equals 3 is corresponding with this factor x minus 3. So it's something still hold along with this observation we have made right there. But once again, but wait a minute, once we have made this observation, isn't that supposedly the same for x equals 2? This is also a 0 in the numerator. X equals 2 is a 0 in the numerator as well. But can this be a horizontal intercept? Okay, can this be a horizontal intercept? I put that question mark there quickly. But the truth now is that the graph we already saw did not list this, did not show this as a horizontal intercept. It was not. Okay, and let's one more time look at the graph right there. Now with the graph, indeed we have a vertical asymptote at x equals 2. Okay, so vertical asymptote in this case, in the earlier problem, we saw that when we had a hole there, when our 0 in the denominator, when one of our 0 or some of our zeros in the numerator happened to be a hole in the graph right there, then we cannot take that. We couldn't take those as a horizontal intercept. And so here we, admittedly, this is a 0 of our, this is also a 0 of our numerator, but this is where we had a vertical asymptote. This is where we have a vertical asymptote on the graph, and we saw that right there. And so, but in the end, hole or a vertical asymptote, it's all about, at this point, we are at a 0. We are at a 0. We have a 0 for the denominator at that point. Okay, so this point here, we found that we recognize that as a 0 of the numerator, but it's now also a 0 of the denominator. And that's another reason why, it's one more time the reason that led to we could not take this as a horizontal intercept. So we put in that reason again. So we found, for the numerator, we found 2 zeros, but we just couldn't take this one. We only accept 3 right here, x equals 3. We took this out. So the reason for that, because x equals 2 is also a 0 of the denominator. All right, it's also a 0 of the denominator. So it looks like we keep getting more firm, and we keep getting more firm and more firm about that rule. It seems like horizontal intercepts, yes, for sure, it happens at the horizontal, it happens at the zeros of the numerator. That's where we turn our focus. That's where we narrow our focus to in order to identify the horizontal intercepts. But then once we have identified all the zeros of the numerator, that won't quite show all the horizontal intercepts yet, because we're gonna have to filter out some of those. It looks like we're gonna have to filter out some of those. So looks like the rule to filter out some of those zeros of the numerator is here. If some zeros of the numerator is also recognized is also recognized as a 0 of the denominator, it looks like we have to rule those out and cannot accept those as a horizontal intercept. Okay, so it looks like we keep getting into that way right there. All right, so now once we've taken that rule, that's general observation, and blend it in with this rule to filter out some of the possible horizontal intercepts to roll out right there, then we're gonna look into the next one right here, a fourth demo problem, and then we should be able to come up with a final solid method. All right. And so now this time I'm looking at how about our function in complete factor form, both top and bottom right here, both numerator and denominator. We're looking at x times x plus 1 all square, okay, and then times divided by x minus 2 times x plus 1. Okay, we had our function here, our rational function here, given completely as completely in factor form. All right, so now in this way, again, let's use decimals to recognize immediately our horizontal. Let's just recognize or estimate our horizontal intercepts. All right. All right, so now on our graphing space with decimals, the graphing utility here, then this is the graph for our function f of x. All right, and now let me adjust the resolution of this a little bit, okay, to put that into finer mode of all these grids right here. All right, so now this graph here seems to have a vertical asymptote. And so, yes, that vertical asymptote is at x equals 2, which is consistent with what we have learned earlier about this graph right here. Or we can apply our skills in finding vertical asymptote and verify that this graph, this function, should have a vertical asymptote at x equals 2. However, let's look a little further at this area right here. Indeed, this graph has a hole. The graph of our function here will have a hole at x equals -1. Okay, let me now show the label. So the hole here, so tentatively it's y equals 0. And so this hole right here is placed right at x equals -1 right there. Okay, and so now, but then it looks like we have another point right here that seems like where the graph is crossing through the x-axis. So now we are clear that a hole cannot be an intercept, even though the hole seems to happen right on the horizontal axis right here. Okay, and so now let me put in the other value right here, the other point right there, to make it real clear. So now we indeed have a solid point being the horizontal intercept. Okay, and now I'm going to show the label for that. So when x equals 0, we have a point going on where the graph is crossing through the horizontal axis. All right, so in that way, let's record down what we have recognized as far as the horizontal intercepts. We found, and then quickly doing a left and right sweep, left and right sweeping through the graph right here. It looks like these are the only place where we recognize some crossing points right there, and some holes. Other than that, there's nothing else special aside from that vertical asymptote right there. Okay. So now on the board, this is what I observed from the graph. I have found a horizontal asymptote. I have found a horizontal intercept at x equals 0. Okay, we found a horizontal intercept at x equals 0. But now as far as being, so yes, this one here is consistent with what we have observed earlier. It is a 0 from our numerator. Look right here in the factor form of our numerator. It's this 0, x equals 0, this horizontal intercept that we listed down here, observed from the graph, estimated from the graph, is consistent with that 0 from the numerator. Okay, but then see, from that general observation we've made earlier, horizontal intercepts are at zeros of the numerator. Then in that, if that's the case right here, then we should have had x equals -1 that counts too, because x equals -1 is also another 0 of our numerator. Okay, but in this case, now notice we had a hole here, so I put question mark here. How come we did not consider this one here as our horizontal intercepts? Because so now we saw from the graph earlier, x equals -1. Okay, was we had a hole there, or in other words, x equals -1 is a 0 in the denominator as well. And then we also had another, as far as domain, we have to be anywhere except these two values right here. And then, or x equals 2 is another 0 in our denominator. Okay, and so in that way, once again, I'm using that same reasoning. We cannot accept this x equals -1 as a horizontal intercept, simply because well, we saw in the picture that we had a hole there. But the real reason here is because x equals -1 is also, okay, this is the reason, that kind of reasoning that made me filter out, okay, this possible candidate for being a horizontal asymptote, a horizontal, this candidate for being a horizontal intercept right here. All right, so x equals -1 is also a 0 in the denominator. All right, so now 4 demonstration problems in a row right there, and then we start being more firm and more firm into the following guidelines. So it looks like any times that we are asked to find horizontal intercepts of a rational function. Now this is only for rational function, what we're about to learn here. Okay, anytime we're asked to find the horizontal intercepts of a given rational function, then the first thing is we're gonna turn our focus to all the zeros of the numerator. That's the first thing we're gonna turn our focus to, within the zeros of the numerator. Okay, so any zeros from the numerator is a candidate. In the way how I see that, it's a candidate to become a horizontal intercept. But then, will that candidate qualify eventually to be a horizontal intercept? We need another filtering factor. We need another filtering criteria right here. The filtering criteria is here. If any candidates, so these are all the zeros from the numerator. But if any of the 0 from the numerator is also a 0 in the denominator, then we have to filter that 0 out. Okay. So and if this one here was also a 0 from the denominator, then we also have to rule it out. Okay. So that I see this sort of like a filtering criteria right there, to filter out the candidates, and only the one that meets, only the one that pass through that filtering right there will become the horizontal, or will be accepted as the horizontal intercepts. And that's now formulate our general guideline for how to find a horizontal intercept right there. Okay. So now on this board, let's write down, let's formulate that that generalization of the as a guideline to find our horizontal intercepts. All right. So how about for finding horizontal intercept? Okay. Anytime finding horizontal intercept, let me put it in the following wording. And admittedly, this is allow me to have my own way of wording it. All right. So now I'm saying unless it's also a 0 in the denominator. Okay, unless it's also a 0 in the denominator. Any value x equals a is a horizontal intercept. Intercept of the rational function f of x if it is a 0, okay, of the numerator. All right. So we want to highlight this. If it is a 0, okay, of the numerator, unless it's also a 0 in the denominator, unless, so this is bringing a side about exclusion right there, okay, unless it's also a 0 in the denominator. So what is it? I'm talking about any value x equals a on the horizontal axis right there. Any value x equals a is a horizontal intercept, okay, of the rational function. If it is a 0 in the numerator, but we have to filter it out, okay, because I'm saying unless it's a 0 in the denominator. So as a hard rule now, as a generality, as a general rule, anytime we recognize a 0 in the numerator, it will be a horizontal intercept, unless it is also a 0 in the denominator. Okay, and so that comes right out from that observation we've made throughout the 4 demonstration problem. Okay, so feel free to pause the video to copy down the notes, the wording I've had here, and then think about that for a moment. And then as you resume the video lessons, we are going to get to the other board and get on with some actual example. All right. All right, so now we are ready for getting into example 6 right here, where we're specifically going to focus on those problems where we are going to find horizontal intercepts. Okay, so I just want to make a final recap of that generalization we've made right there. So it was a worded generalization, and it could be lengthy for somebody, it could be too wordy for anyone, but the main idea now is that first thing, in order to find the horizontal intercepts on any rational function, we just simply need to focus immediately our attention to those zeros in the denominator, to those zeros in the numerator. Okay, and then from that point on, once we have found all the zeros in the numerator, okay, those will be candidates for becoming horizontal intercepts. Okay, but then we're going to have to filter out those candidates where they also appear to be the zeros in the denominator. That's the idea. So sort of like step 1, we're going to find all zeros in the numerator. And then once we've found all of those candidates, we're going to start filtering out any of those that also appear to be the zeros in the denominator. That's the idea. So we got a clear guideline of step 1 and step 2. And that's why, again, in worded statements, it says that's what it said right here, unless it's also a 0 in the denominator. Okay, otherwise any value x equals a is a horizontal intercept of the rational function if it is a 0 of the numerator. And so that's why, like I said, we first going to focus our attention to the zeros in the numerator. All right, so now let's really get into example 6 right here. All right, so now let's find, in this case, the the worded instruction for example 6 is quite straightforward. Find all, because for horizontal intercepts we can have multiple, okay? So find all horizontal intercepts. All right, find all horizontal intercepts of the given rational function. All right, and so now let's look at the first one of ours right here. Okay, so how about we are going to have R of x to be, and now I'm looking at about x squared minus 7x plus 6 over x minus 3. All right. R of x equals x squared minus 7x plus 6 all over x minus 3. Okay, so now, just like what I highly recommended earlier in the demonstration problems before I got into this formal example here, it is now highly recommended that we factor out all numerator and denominator, both of those. Okay, so I'm not going to rush into finding zeros or anything like that. I am going to just simply factor out, because now what I noticed, our rational function here, the numerator was not factored out yet. The denominator is admittedly only one single linear factor. So there's nothing to factor here any further. Okay, but now I realize that I need to factor out the numerator. Okay, so now it's going to become x minus 6 times x plus, and I mean x minus 1 here, and then all over x minus 3. So now we have completely factored out our rational function in both numerator and denominator. All right, so now right here last, this is so like I said, that logic here is we first have to find all zeros of the numerator. First have to find all zeros of the numerator, but also we're gonna identify among those candidates, we're gonna filter out those being also the zero in the denominator. So have a thought for a moment right here. Have some thinking for a moment right here. That means we in the end we're still gonna have to find zeros for both numerator and denominator. And that's the reason why it is highly recommended that we factor completely both numerator and denominator, because we need to, the method I'm about to show that's based on this generalization right here, we need to list down completely all zeros of numerator and zeros of denominator. Okay, and now allow me to show in my personal style the following the approach right here. So now I'm gonna list down right here zeros of the numerator, okay, colon right here, sort of like, and I'm keeping that as a chart right here. We can keep that as a chart, and then in this, underneath that, I'm gonna also list down zeros of denominator. All right, and so now for the numerator, I found right from this numerator expression, which is now in factor form, I found x equals 1 and x equals 6. X equals 1 and x equals 6. So now I'm going a little bit improvised right here by x equals 1 comma 6 right there. Or you can write it x equals 1 comma x equals 6. Okay, but that's now one complete list of all zeros of the numerator. I'm not saying that all of these are horizontal intercepts. We need to start filtering out if there's any possible candidates among here that's also a zero in the denominator. So in that way, now we have to also list all zeros of the denominator. So from the way how it looks here, after we have completely factored the denominator, the only zero for the only zero of the denominator is x equals 3. All right, so now this candidate pass to be a horizontal intercept simply because it's a 0 in the numerator, but it's not a 0 in the denominator. All right, so that one passed. All right, x equals 6 also passes to become a horizontal intercept for this rational function simply because it is, yes, it's a 0 in the numerator, and it's not among the zeros in the denominator. All right, and so in this way now, so this method of mine that lists out all zeros and kind of matching them to filter out the ones that's being in both rows right here, a row for the zeros in numerator and a row for zeros in the denominator. This is sort of like a one personal approach I use right there. The method is already introduced in that generalization, but this is just the way how I approach that. Okay, and it's make things really solid, clear for me. Okay, crystal clear for me when I was a student myself doing this. All right, so in that way, now we're making our final conclusion for this particular problem. All right, so now in the end, as far as horizontal intercepts, okay, this time we found 2. All right, we found x equals 1 and x equals 6, x equals 1 comma x equals 6. I believe I said this in some of the earlier lecture, but it doesn't hurt to repeat again. But when it comes to horizontal intercepts, it becomes a tradition that we only need to list the x value. So here there are 2 x values, x equals 1 and x equals 6. Okay, but more often when it's vertical intercepts, then we list both components, the x value being 0 and the y value being something. Okay, but then for when it comes to x intercepts, maybe because due to that fact that we may have multiple x intercepts or horizontal intercepts, that's the reason why for convenience we only list the x values or the horizontal values like that. All right, so here I'm talking about we're having 2 horizontal intercepts found at x equals 1 and x equals 6. That's our final answer for this particular problem right there. So to reach that goal that we're gonna, in every problem, we're gonna reach for that goal to go side by side with a graphical view right there, with a graphical understanding, so that we can use the graph to confirm. So this time you can see we already finished our problem and completely without a graph. But it would be a good idea so that we can swing over to the graph and use the graph to confirm our results right there. All right, so now on my empty graphing space with decimals right here, allow me to spend some time typing in the equation of the function. All right, so this is the graph for our rational function x squared minus 7x plus 6 all over x minus 3 right here. Okay, and so in our understanding that we have learned previously, then this function surely has one vertical asymptote at x equals 3. And since the vertical asymptote is not the main focus of our current discussion topic right now, I'll just simply say it, and then you have your way. You have learned enough the understanding to verify what I'm saying here, what I'm showing here. All right, so we do have a vertical asymptote at x equals 3. All right, and now we purposely want to use the graph. Our purpose for looking at the graph here is to confirm our results that we found on the board earlier, that x equals 1 and x equals 6 are the 2 places on the x-axis, on the horizontal axis, where we have horizontal intercepts. All right, so you already saw that on the graph right there. And now let's look at that one more time. And yes, the graph is going through the horizontal axis at x equals 1 right here. And let me pop in that point right there. All right, so this is the first horizontal intercept right here, and the label is showing that it's at 1, 0. So of course, y value or vertical value is 0, x value is at 1, horizontal value is at 1, consistent with the results we have found. And now we have another one at about here. So let's use the graph again to pop out that point. So now the graph is showing 6, 0 to be that particular point like that. All right. And so that is how we have found the horizontal intercept without using the graph. That's the solid method like that. All right. So now let's look into another problem in this particular example. And now for the rest of this example, it doesn't matter how far, how many more problems I'm putting in. What matters for us is simply just the main thing we're doing here is just repeat the steps I have done in part A like that. All right, on every different function that's given at us. So now part B right here, let's look at how about R of x to be, and now I'm looking at how about x squared minus 5x plus 4 divided by x squared minus 3x plus 2. Okay, x squared minus 5x plus 4 divided by x squared minus 3x plus 2. All right, so that's our rational function. It's not completely in factor form yet for both numerator and denominator. So highly recommended as a first preliminary step right there. Highly recommended practice. Let's completely factor the numerator and the denominator. Okay, so now I'm putting that in factor form, the x squared minus 5x plus 4. In your experience with factoring, you can easily verify me this. X minus 4 times x minus 1. That's how I factor out this numerator polynomial. And then now I'm going to go ahead and factor out the denominator polynomial. So now it's in your factoring experience, you can also verify what I'm doing up here. X squared minus 3x plus 2 is factored into x minus 2 times x minus 1. I only set to factor, but I never set to simplify immediately right after we factor, because I understand some of you viewing this lesson is already seeing some common factor where we can simplify, but that's not the point. The point is to factor completely so that we can see all factors, all linear factors, distinct linear factors that's responsible for giving all the zeros of our need. Our need is to find the zeros, all zeros in the numerator and all zero as well as all zeros in the denominator. All right, so in that way now, once I have successfully put my rational function here in factor form for both numerator and denominator, I'm gonna go ahead now to make that comprehensive list again. So I'm listing down, so as far as I'm looking at zeros of the numerator. All right, and then I'm going to create another line right here to list down all zeros of the denominator. All right, the three zeros of the denominator. And so, and recall again, multiplicity of any of these zeros does not matter, because when we list down zeros, we only list down the distinct zeros corresponding to the distinct linear factors which appeared in our numerator and in our denominator. Okay, and so in that way, for the numerator, I see only two zeros. One of them is corresponding to that x minus 4 factor. The other one is x equals 1, corresponding to this x minus 1 factor. So once again, one of them is x equals 4. The other one is corresponding to x. The other one is x equals 1. So this time, unlike the earlier problem, I'm writing down the formal work for here. X equals 4, corresponding to that. X equals 1, corresponding to x minus 1. Okay. Now let's list down the zeros of the denominator. Now I see x equals 2. Now I see x equals 1. All right. So now, once we have listed that, the answer is clear. The answer is clear. So the candidates competing to become horizontal intercepts are here. These are the candidates. And we're going to have to filter out some of those candidates may not become horizontal intercepts. Which one are they? This one passes simply because, yes, it's a 0 in the numerator, and it's not a 0 at the same time. It's not a 0 in the denominator. It's not among the zeros in the denominator. So that's why this guy passed. All right, we found one horizontal intercept right here at x equals 4. What about the other candidate? Yes, it's a 0 in the numerator among this list right here. But sadly, it's also a 0 among the zeros in the denominator. It's a 0 in the denominator as well. All right. See, I pinpointed right there. So this guy indeed failed. X equals 1 as a 0 in the numerator failed to be the horizontal intercepts. All right, so that's all we have. So now at this point we are ready to make our final conclusion. So as far as horizontal intercept, all right, I have only found x equals 4, and that's the only one for this particular rational function. All right, and again, let's quickly hop over to the graphing utility on my computer station right there, at my computer station, to look at the graph and double confirm our result right there. We have already finished our problem completely without looking at the graph. Okay, completely without the graph. But let's use the graph to double confirm what we have found right there. Okay. All right, so now with our empty graphing space in decimals here, the function we have has the following graph. All right, so there we go. This is the graph for our function. And so in our understanding at this point right here, we know that we expect that this graph, this function, and we observe right here in the graph as well, we expect that this function has one vertical asymptote at x equals 2. X equals 2. Right there. That's our vertical asymptote. All right. And then, aside from our vertical asymptotes, this graph is indeed going to have a hole at x equals 1. And this is the reason why, as far as horizontal intercepts, we found only one horizontal intercept right here at x equals 4. And that result is confirmed by the graphing utility I'm using here with decimals. All right. All right, so let's now look at another rational function, and we can call that part C of our example. All right, so here, how about I'm looking at R of x given as, how about allow me this time to make it easy for everyone viewing this lesson right here, then I'm going to deliver the function already in factor form completely in both the numerator and denominator. So how about x minus 5 times x minus 1, and then in the denominator we have x times x minus 1 all squared. All right, so x minus 5 times x minus 1, and in the denominator I have x times x minus 1 all squared. All right, so we don't need to spend our efforts in terms of finding the factor form of numerator and denominator because it's already given. All right, so now let's search for the horizontal intercepts by first finding all all zeros in our numerator and also the denominator. Okay, so now in that way, here's how I'm seeing it. Zeros in numerator. All right, the 0 of our numerator. That will give me the following. I found one candidate corresponding to that x minus 5 factor here. So that has to give me a 0 in the numerator at x equals 5. And I will have another one at x equals 1, which is corresponding to that distinct factor, the linear factor in the numerator, x minus 1. All right, so I've found two candidates for being a horizontal intercept. But now, we're not going to conclude that, hey, these are our two horizontal intercepts. We have to see if any one of these gets filtered out or not. Okay, and so now we're going to look for zeros in order to filter out properly. We're going to look for zeros in the denominator. And those are, see, again, we have some multiplicity here, but what matters about the zeros is we only need to look for the distinct zeros corresponding to these distinct linear factors. Okay, so now I have one at x equals 0, and I have another one at x equals 1. I purposely wrote them in a way that they line up in a column right here. Okay, so now the answer has become clear. All right. So let's look at, so again, all candidates for being horizontal intercepts are the zeros in the numerator. So these are all the candidates right here. But some candidates will pass and become the actual horizontal intercepts. Some other candidates may fail because they also appear to be a 0 in the denominator. All right, so now let's go through all of these candidates here one by one to determine who must be filtered out. Okay, so this first one, are we going to filter it out? Well, x equals 5 is a 0 in the numerator, but it's not found. X equals 5 is not found among the zeros of the denominator. So this first one here passed. All right, let's move on to the next candidate among the zeros of the zeros in the numerator. The next candidate now, it is a 0 in the numerator, but it's also a 0 in the denominator. All right, so in that way, this candidate is filtered out. All right, so that candidate failed right there, got filtered out. We only accept this one here as the horizontal, horizontal intercept. All right, so in that way, my final conclusion is as following. So as far as horizontal intercept, all right, as far as horizontal intercepts, and we never, I mean, here I'm always writing intercepts in optional plural right there, because there are times it's only one intercept, there are times it's multiple intercepts, okay? And there could even be times where there's no intercept, horizontal intercept at all. And we will hit to some of those problems among our example problems here as well. Okay, so this guy failed, only that guy passed and became the horizontal intercept. So now x equals 5 is our only answer for that. All right, that's how it is. Nice and short little method like that. All right, and once again, let's confirm our result with the graph on Desmos graphing utility. All right, so now on my empty graphing space with Desmos, the graphing utility here, this is the graph for our function. And this graph is for x minus 5 times x minus 1 all over x times x minus 1 all square. All right, so in what we have already learned, and this graph, and of course, according to the way how it looks right here, this graph has two vertical asymptotes, indicating these are the zeros in the denominator. So one of them is at x equals 0, right at the vertical axis right here. And let me put that in. That line right there, that vertical line, x equals 0, or which is also the same as our y-axis. That's our vertical asymptote, one of them. We have another one at x equals 1. All right, and so now two vertical asymptotes, and our graph is asymptotic asymptotic around these two lines right here. Okay, so with a quick sweep through from the left and right, I see that on the left side right here, it looks like no matter how far I sweep out to the left-hand side, the graph in red will keep staying below the horizontal axis. So I can see that there's no horizontal intercepts back there, and we already saw the result confirmed. So needless to do too much of those sweeping work right there. Okay, so let's look at this area right here. All right. So now it's shown that the only place where it's crossing, according to our calculation, our actual calculation, because looking at the graph, it could be a little hard to read sometimes. All right. So the only place where the graph crossed through the x-axis, the horizontal axis, is when x equals 5. Okay, when x equals 5 right here. That is consistent with our calculation result. And so let me show that point here again. All right, so x equals 5 right here as a solid point right here. And let me also show the label, the numerical label. So 5, 0, horizontal value 5, vertical value 0. Okay, so this point confirms our calculation, and we found, and there's no other one. When x equals 1 that we saw on our list earlier on the board, x equals 1 is acting as our vertical asymptote right here. All right, so that's why now consequently it turns out there's only one horizontal intercept at x equals 5. All right. All right, so now let's look at another problem right here as our part D of the example, another rational function. And I would like to bring this to your attention, for anyone viewing this lesson right here. So we mostly focus on those where we found the zeros for the numerator successfully. Okay, but there are times out there where, let's look at a function. How about r of x here equals simply 5 over x minus 1 times x minus 3. It's a rational function, completely fine looking, completely legal to be a rational function in fraction form. The only thing is in the numerator it's a constant, already a constant, and in the denominator it's just some expression, and I have already put that polynomial in the denominator in factor form. Okay, so now let's find the horizontal intercept of this function. Okay. And so now, since the numerator is being a constant, and we already knew that this constant is not equal to 0, okay, and there's no other x or anything like that, so we can't really factor any further. This constant, it's by itself. There's no factor. There's no factoring that can be done for this numerator. And so now we can just get straight into the point here. So as far as 0 in the numerator, okay, 0 in the numerator. And then, yes, I just want to lay it down, even though some of you may already see the answer so clear, but allow me to just always lay it down to the foremost steps so that you can see the repetition of the steps, so that you can continue that to continue using that for further problems. Yeah. So zeros in the denominator. All right. It's easy to see the zeros in the denominator. Let's just write it down immediately. X equals 1 to be corresponding with that x minus 1 distinct linear factor in our denominator. We have another one, x equals 3, which is corresponding to that x minus 3 distinct linear factor. And we have found all zeros in the denominator. Okay? But now as far as the 0 in the numerator, if we just look at this polynomial on its own as a constant function, f of x equals 5, c of x equals 5, or r of x equals 5, a constant function. This constant function, the way how it looks is like this. It's one horizontal flat line at 5, at y equals 5, like that. All right, so in the way how the picture looks right here, it will not cross. There's no 0 for this line right here. All right, there's no x values that cause this line to equal 0 because it will run parallel with the with the x-axis. Y equals 0 is the x-axis. This line will run parallel with that permanently once we gave that definition. Okay, and so in that way, now I can just saying it out loud. I can just say it out loud. None. We have no zeros in the numerator. So think about, we're looking for the candidates, but there are times that we don't even have any candidates. We don't even have any candidates for the horizontal intercepts. So we don't need to do the matching up thing. We don't even need to do that. Our answer now is straightforward as far as horizontal intercepts. Okay. Now the only answer, sadly, for this function, none. 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 All right. So once again, let's confirm. Okay. So I talked about the candidates just like that. We found none, no zeros in the denominator. So the simple answer here for horizontal intercepts, none. Just think about, in some of these, some of those election years, right there, we have no candidates running for an office position. Then for that particular office position, we have none. Okay, we probably going to have no one in office for that particular position. That's a theoretical scenario. Okay, so just like this, looking for horizontal intercepts, we found no candidates, none. All right, so now in the graphing space with my graphing utility. All right, this is our graph for this function. This is our graph for that function. Okay. Yes, admittedly, we have two vertical asymptotes. One of them is at x equals 1, and the other one is at x equals 3. We have two vertical asymptotes. But now, in the way how it looks, see, quickly as a brief sweeping left and right here, we recognize nowhere on the left and right here that we found a point where the graph is crossing through the x-axis. So just consistent with the results we have found right there, there's none. There's no horizontal intercepts for this graph. All right. All right, so this last problem I'm bringing into this example 6 right here is optional. Really, it's optional, but I still would like to bring it in so that it strengthens your skills to decide. Sometimes we have no zeros in the numerator at all, but it's a little tricky to decide that we have no zeros in the numerator. Okay, no candidates to run for horizontal asymptotes. Okay, so let's look at part E right here. So if you feel like this is too optional for you, then you can skip this example. But at any other points where you need to learn some extra details, you can roll back to this particular example 6 and learn from what I'm doing here. So R of x, a rational function. Let's say I'm going to look at x squared plus 4x plus 5. Okay, it's a quadratic in general form. Okay, it's a quadratic, it's a polynomial in the numerator, but in general form. I didn't write that in factor form this time. Okay, the denominator, awkwardly enough, I'm giving that in factor form. X minus 1 times x plus 5. Okay, I came up with that's really on the go right there, randomly out of my own creativity. All right, so there we go. We have our rational expression. So now, since I triggered your attention here a little bit, that I put this numerator in the in the general form, not the factor form. So just like how you were seeing that through the earlier problems of this example, we're gonna start getting into factoring this. All right, and then pause the video, take your time to make your attempts on factoring this. And then we're going to resume after you have experienced something with the factoring of this polynomial. All right, so at this point, I hope you've had some clear thoughts about this numerator over here. The reason I gave that here in general form because at least in my experience, I'm not good enough maybe, but I cannot find the factor form of this polynomial. I cannot find the factor form of this polynomial. Okay? Simply because now if I see this as a scratch word, think of this x squared plus 4x plus 5 as a quadratic equation. We have learned that famous technique for a quadratic equation, and I also brought it in to some of our other lectures a few times already. This is A equals 1, B equals positive 4, and C equals 5. In the world of, now we're strictly looking at this polynomial as one function in the world of the quadratic functions. A equals 1, leading coefficient, B equals positive 4, linear coefficient, and C equals 5, the constant value. Okay, so now this is what I observed and I noticed right here. The b squared minus 4ac, which I brought in some other lectures right there, and now I'm using it again. But this b squared minus 4ac trick is only, I shouldn't call it trick, it's just a technique right here. This b squared minus 4ac technique is only for the quadratic. Okay, but that equals, laying down the calculation here, we're looking at 4 squared minus 4 times 1 for A times 5 for C right there. That gives me a negative 4, because that's a 16 minus a 20, that's a negative 4, which is a negative value. So recall again from our past understanding, anytime the b squared minus 4ac from a specifically quadratic function, then this negative b squared minus 4ac verifies that we cannot factor this. We won't have a factor form, a linear factor form for that. There will be no successful linear factor form of this polynomial. Okay, so in that case, that means, so now getting into searching for the zeros in the numerator, okay, and searching for the zeros in the denominator. It's easy to see that the denominator has 2 zeros. One of them is at x equals 1, the other one is at x equals negative 5. So clear and so direct. Okay, but now as far as the zeros in the numerator, again I'm saying none. I'm saying none because, see, specifically for this function as a quadratic, this polynomial in the numerator as a quadratic, and breaking it down with the, with the a coefficient, the b coefficient, and the c coefficient, then we discovered that the b squared minus 4ac turns out to be negative. And so having a negative b squared over minus 4ac is a way to guarantee, to confirm that this equation, this polynomial, this degree 2 polynomial has no zeros. Has no zeros. So that's why I'm saying that zeros in the numerator, none. So again, just like part D that I've done earlier, as far as candidates running for horizontal intercepts, we have none. Okay? And so now, as final conclusion for horizontal intercepts, all right, for horizontal intercepts, we have none. All right, that's our answer. Okay. We have no horizontal intercepts for this particular rational function. So as far as the logic of how we get the problem done, it's just exactly like the problem in part D where there was no intercepts. But I would like to bring this in, and I mentioned that earlier, I want to treat this problem here as an optional problem. So if you feel like you didn't need that before I got into that, feel free to pause the video or even exit out of this particular example right there, or rush over it. But then at some point, if you feel like you need that experience, you can watch this one a little more thoroughly. Okay. And so now, all right, and again, let's turn over to our graphing utility with Desmos here to confirm the result we have just seen on the board there. So this is the graph for for x squared plus 4x plus 5 all over x minus 1 times x plus 5 in the denominator. Okay, so clearly we have two vertical asymptotes. In our learning experience up to this point, we can quickly realize that there's one asymptote at x equals 1. That's one of them. And the other one is at x equals negative 5. All right, but now other than those vertical asymptotes which came from the zeros in the denominator, then this graph has completely no intercepts, no intersection point with the horizontal axis at all. All right, and so that's how I see about this. And see, even though this part of the graph comes real close, but in the end it's still making some difference, and then it turned away.